Cool. Yeah, so let us continue where we left off. Yeah, I guess I have a couple notes to say, as usual, to begin with. So I just wanted to point out that I made a sort of big mistake throughout that you should have noticed, or maybe not. Anyways, now we know. So there's been multiple times where we've dealt with these multivariate functions like g of w vector. And then I was writing things like, oh, if you take the partial derivative of g with respect to wj, I was then writing this is only a function of wj. This is, of course, not true, because when you take the derivative, sometimes you get a function of the other variables, even though after you hold them constant, they still might appear. So anyways, the correct thing to write is something like this. Well, exactly this, where here this thing is actually a function of w, right? Yeah. So this comes up with the loss function, stuff like this. Anyways, this was just like in the last lecture. I said this maybe once or twice. In the notes, it's written correctly, like in the course notes. So anyways, from now on, this is gonna be correct and stuff. And I'm gonna point that out in 1 second from the last lecture where that came up. And also, I'm just gonna go over a quick example of this like closed form linear regression thing. So let's just hop back very briefly to this closed form stuff before we go back to gradient descent. Okay, so you might remember we were doing this like linear regression stuff, and we were trying to find the best possible predictor f and stuff like this. Okay, there was a bunch of these steps, and then I just said all we have to really do is just solve this kind of problem here. And the way we would do that is we would just take the derivative of this and set it to 0. And so then I wrote out some different ways. You can look at this. Oh, let me make this bigger. We can look at this thing. And then here I was writing something like the derivative of this estimate with respect to a specific index of the like weight vector. And then here I had previously written wj. So now I've changed it to the actual vector w. So each one of these things is a function of w. And clearly that's the case, because when we look at it, we get something like this. And this has like the w vector in here. Okay, so it clearly depends on the whole vector. Anyways, just an important note for everything going forward. So it's been changed everywhere in these notes that I've uploaded, and in the notes today and stuff, you're going to see this. Okay, and then all I wanted to point out is that we got to this algorithm where basically all it did was just solved some linear algebra problem. And that thing was something like compute this w, this weight vector, right? And then output the predictor that uses this weight vector in exactly this way. And that was like written in this like pseudocode. You're going to get to implement it in the assignment. But then I thought I should maybe like point out like, what does this actually look like visually with data, which you'll also get to plot in the assignment. Well, it looks something like this. So this is a quick little example I added that I wanted to just mention. And this is just like super high level. But imagine you had just like one dimension, so a feature of one dimension. And then remember, like x will then be r to the 2, because we always think the first index as being fixed to the number 1. Okay, but the point is, if you like think of it as, for instance, the number of rooms is your feature, and then you want to predict the price. Well, what is this algorithm doing? What it's doing is it looks at your data set, which is the following. These are depicted by these like black points everywhere. And then it's finding the function, this predictor, the predictor function, which fits the data the best. Okay, and it fits it the best in terms of like this squared loss. So you would actually be measuring like these distances to every one of these points. And basically you're picking the line, which would be this purple line, that fits the data the best. So this would be like something, this would be like what you're predicted, what you actually end up outputting, this w vector hat. And it would look something like this. So this is what you would have learned from the data. You would have learned this like line that best fits the data. Okay. Yeah. Yeah, so okay, I can so the question kind of was like, what happened from we took this derivative with respect to wj, but then we ended up getting a w hat at the end, I guess is sort of the question. And the answer to that is if we maybe go back to like the simpler setting where we just had this g and there's nothing about machine learning and stuff yet. I said that the way you solve for this w vector, right, which has all these indices, is you solve for each index 1 by 1. So that would mean solve for w1, w2, w3 up to wd. And then the question just is, how do you solve for each one of those? Once I've solved for each one, I just put it into a vector. So then I just need to solve for each one. And the way you do that is you just set the partial derivative with respect to each w. So you do it for w1, w2, right? This is just the general form for wj. And you set it to 0, and then you solve. So that's the general way to do it. And then like, how did it look here? Well, what it looked like here is that now instead of g, we have L hat. We took its derivative with respect to wj. And then what we ended up getting, okay, we solved for things and stuff like that. We set it to 0. We rearranged. We got something like this. And this is the equation that needs to hold for every single j. So it needs to hold for j equals 0, 1, 2, 3, up to d. And then I just explicitly wrote this out. So like, this is the case. So maybe I write it here. This is the case when j was equal to 0. And then this is dot, dot, dot up to j equals d. So then I had a system of d plus 1 equations. All of these had to hold true. And then there's some interdependency between them, right? I need to solve for w, but then notice that this w has to hold, like this equation needs to hold for w, but then also the one in the middle needs to hold, and all the way up to these. So this is like, there's a giant system of equations, and you need to isolate for this. And this becomes a, like, if you try to do a 1 by 1 and isolate here, then you need to plug in that result back into here, and so on. And anyways, the simple way to do this is you learn this in linear algebra, and for this course, you just need to know that this can be done, which is that you arrange things into what looks like a matrix times a vector, your unknown vector, equal to some other vector. And then it turns out that this has like a very standard solution, which is just you multiplied by, like what happened here? You multiplied both sides by A inverse, right? And then this thing, of course, is just the identity. And so you just ended up with the W vector, this thing, your unknown thing, is equal to the following. And yeah, but that all came from this original story that you need to solve for each individual index. And then you got the system of equations, and then yeah. That's the story. And maybe one thing to point out is that the reason why this looks so much more complicated than the example here that I gave is because here, when you take the derivative and set it to 0, you notice that the corresponding like function you get for the derivative is just a function of w1. It does not depend on w2. So you could just immediately solve for what w1 is from this equation. For w2, similarly, you solve for this equation. And you don't have to like plug things in between the equations. There's no dependence between the equations, which is what we had in the machine learning case, which made things a little bit harder. But that's the main difference why things might look different. Okay. Anyways, that's the closed form stuff. So now we talk about how to solve this with this thing called gradient descent. And before we get into machine learning world, we build up our like gradient descent knowledge in general, like math and stuff. So like there's nothing to do with machine learning for the next maybe like 50 minutes or so. And then we'll see how it all relates to machine learning again. Okay, so I quickly remind you what happened. The story was something like, can we always just find a closed form solution? Which means, can we just always take the derivative and set it to 0? And then we, like with a quick example like this, which was if you had w squared, this function plus e to the w, if you had that function and you tried doing this process, you first check it's convex, which it clearly is. Like visually, you can see it looks like this bowl. But then if you try to take the derivative and set it to 0, you get this expression, which has no closed form solution. And what I mean by no closed form solution is I can't write what w equals in terms of what we call like elementary functions. So like in terms of the squared function or like the cosine or reciprocal, like you can't. So this is what we mean by no closed form solution. But it turns out we can like approximate the solution. That's what this gradient descent is going to do. It's going to like approximate what this w. Okay, so visually you can see what w star is. Like that it's somewhere down here, but you don't know the actual value, and you want like somehow to calculate this value. And so we're going to like approximate it with this thing called gradient descent. And that is what we were starting to build up on. How do we do this? Like, how do we approximate this minimum point w star? So if there's anything you got to remember for this lecture, it's you're trying to find w star, as always, with optimization. Okay, so yeah, we started with, like, the story was, okay, if g of w doesn't have a closed form solution, maybe we approximated with a function that does have a closed form solution. Okay, and then if our approximation is good, we just find the closed form solution for that approximation, and we say, okay, we have something that's a good approximation. So we said, okay, approximate g of w with something called like this second order Taylor approximation. Why is this a good like approximation to choose? Well, it has a closed form solution and it's convex. So you can just use the techniques we used before, which in particular was like set the derivative to 0 and solve. Okay, so visually, this is just showing what the approximation looks like of the function. So black is the original function we want to approximate. Orange is our approximation. Okay, so for the approximation, another important thing is that you always have to choose a point at which you're approximating at. So for this second order Taylor approximation, we chose to approximate at W naught. Okay, this is going to be very important. Like, and the story is that if the point at which you're approximating at, the approximation is quite good, and further away, it's not as good. So here, W naught, we just chose any W naught. Here we chose W naught equal to 1. And we can see that the orange function is pretty good around this area, like between W naught equal to 1. It's a pretty good approximation. But as we get further away, like over here, you can see that it's not anywhere near as good. Like it gets worse and worse. And similar if we were to draw the plot like to the right. Okay, so the point at which we approximate is important, but nonetheless, we still get an approximation of the function. Okay, so we had this function, this orange function, and then we said, let's find its minimum point, and then that minimum point is probably close to the true, like W star. And so how did we do that? Well, we had this approximation, we took its derivative, which is the following, set it to 0, and then solved. And then we got this general equation. This will hold true for like any function. And then you just solve for the point, W. This W gives you the minimum. And what I mean is it gives you this minimum point. Okay. Visually, like it looked as follows, which is you get, if you solve that equation, you get this green X. Okay, and so now we start today's lecture. Okay, so like we got this green X. It has this equation as follows, and I'm just gonna write something, which is we're gonna call this W above W1. Okay, and like this is for, you'll see why this notation makes sense. Like very, very soon, you're gonna see why it makes sense. But you can already kind of see, like we started with some initial point at which we do the approximation, W naught. Then we had a function, this orange function. We then find its minimum, and that gives us like a new point, W1, right? And notice how this new point is closer to W star than originally W naught was. Okay, so at this point, we could just stop and say, okay, like W star is approximately equal to W1, and maybe we have a minimum, like we have some approximation to it, right? Or this is the observation we make now, which is that we wanted a good approximation to the original G of W. And so we had to make a guess at some point, like W naught, and we had a good approximation around W naught. But notice how we got farther, our approximation was worse. Well, now we have a new point, which is called W1. We know W1 is going to be closer to W star, or like at least I'm telling you this, it's going to be closer because that was like our goal. So guess what we can do? We can redo the process that we just saw, except now we approximate G of W, not at W0, but at W1. And by that logic, like the before, like now our function is going to be quite good around this region of W1. And that's much closer to W star. And so if we repeat the process, we're going to get something that like is going to get closer to W star, and then we can do this over and over again. So let's see what that looks like. Okay, so this is like basically what I said, which is that like we can approximate GW again, but at not W0, but at W1. Okay, and this thing is closer to W star than W0 was. So what do we get? Well, okay, like I write it, I just copy and paste the thing, which is, this was our equation for the approximation at W0. So to be very explicit about it, now we're going to have an approximation at W1, and guess what? We just replace all these zeros with ones. Like that's the only thing that changes. Okay. Great. So if then we continue with the previous example, we can visually see what our new approximation looks like, and that it is indeed better than the previous version. Okay. So the green thing is this G of W1. Remember, we solved for W1 above, it was 0. That was this point. 0. Okay, so we're going to do the approximation at there, and we get this green function. So this is this green guy here. And notice that around W1, it is quite good at approximating g of W. So guess what? Now if we find the minimum of this green function, right, this new approximation, you can see that this minimum is going to be very, very close to W star. Okay, so we can do that again, and like, guess what? The equation is exactly like the same as this. And I copy and paste again. So then we can minimize. The equation now becomes, okay, this is 2, this is 1, this is 1, and this is 1. Right? Now all I need is that I need the first derivative of g prime, like of the original function, but now I just plug in W1 instead of W0, and similar to here. Okay. So guess what? That's like what this next plot gives you. And I didn't, instead of working out, oh, what happened? Instead of working out the steps of this, like, you can take these derivatives and solve at home, I guess. But the story is that if you do this, like this above calculation, with W1 plugged in, and what do I mean by W1 plugged in? I mean like plugging in W1 equal to 0 from the previous example. If you evaluate these things, you get the following, which is that W2 is -1/3. And the important thing to remember, like to see, is the visual interpretation. So all we did was solve for the minimum of the green function. That minimum is this purple x here, and you can see it is very, very close to the true minimum, which is that black x, W star. Okay. And so, like, yeah, we've gotten closer to the W star, which is the black W star, which we're trying to solve for. And it turns out that, like, guess what? You can reuse W2 as your initial guess and do this step again and again and again. And okay, so what you get is, in general, your WT plus 1, right? Your previous approximation you had, and then minus this like equation that we had for the update. Right. And so here's what the story is, which is that WT plus 1 approaches W star. This just means it gets closer and closer to the true W star as t goes to infinity. Okay, so the more steps you do of this, and then I'm using this word steps, but like iterations or whatever of this process, then you get closer and closer to W star. Okay, and you can stop at any point you want, right? The more steps you do, the better you're going to get. But like in reality, you only have like so much computation and stuff you're going to run. So you make like a choice. I want to stop maybe after 10 iterations or something. But you can see already in this like simple case, 2 steps is like pretty, like you get pretty damn close. You can do maybe a 3rd step and you're basically a W star. Okay, so this is a very important idea. It might seem very simple, but this is almost at the very heart of all of machine learning. And in particular, okay, so that's kind of this, and I said this is called 2nd order gradient descent. So what is up with this like 2nd order stuff? Okay, the 2nd order thing was the fact that we approximated with a 2nd degree polynomial, 2nd order polynomial, right? That's what all these parabolas are. Okay. So that's kind of the end of 2nd order gradient descent. Now it turns out that there's something called 1st order and 1st order gradient descent, which we're going to do next. But before that, I answer a question, which is, sir, please can you tell me what W0 and W1 he and how we are finding it through gradient descent? Okay, I am assuming that they're just asking what W0 and W1 and stuff are. But yeah, so like, to remind you, we started with the function g of w, which is the black thing. We approximate g of w with some other function. We call this like g subscript at the point you approximate, W0. That's the orange thing. And then W1, okay, so you approximate this g function with this orange thing, and you approximate it at W0. So W0 is the point at which you're doing the approximation at, right? So when you do these Taylor approximations, you say, I have an approximation at or like for the point W0. And then W1 is the minimizer of this approximation. So it becomes like this, exactly this. So this plot kind of says it all. W0 is the point at which the approximation is made at, while W1 is the actual minimum of the approximation. Okay? Then what do? What you do is you then create a new approximation where you approximate at W1. So now you can, this green thing is your approximation, your quadratic approximation at W1. This thing is good around W1. And then W2 is just the minimum of the approximation at W1, okay? So like you're doing this iterative thing where you're finding the minimum of one function, then using it as kind of like the approximation point of another function, and then finding the minimum of the new function, and so on and so on. Yeah. Oh, I just replaced W1 with the value of 0. All I did is plug it in. Like it's kind of a pointless. Honestly, I probably shouldn't even have this here. It's just a W1, and W1. I like in the example, I pick a point for W1. Before the example, this is just a general formula, right? Like you can pick any W. Like okay, well, like you can't pick. You first start with W0, then you iterate, you get W1. But yeah. So this W1 was based on the fact that we started with the original point W0. If I change W0 to say like 10, right, then I would be approximating like all the way down there somewhere. And then my W1 would be different, and my W2 would be different, and so on. So really, you always begin, there's the starting point where you have to make an original guess, which is like, where are you starting your approximation from? And then from there, you like move closer and closer to the true minimum. Yeah.
Zero is just like a random point that we begin.
That's right. And in machine learning, this is like called the random initialization and stuff of things. Like we're gonna see this. Like you're sent like in the machine learning, like the algorithm's coming, the gradient descent stuff for machine learning, and they're literally W0 is going to just be a random initialization. Just any random, and at this point it's just one number. Later it's going to be a vector, but you're just going to randomly initialize a vector. Turns out there's a lot of like, we're not going to cover in this class, but there's a lot of like details about how to best pick this initialization and which one's best and stuff in machine learning, but that's like a whole other thing. But yeah, so like the very elementary way to think about it, you just pick any random point because you have known better knowledge of where to pick it. And then from there, you just iterate to the minimum. Okay, because like how could you, like without any knowledge of the function beforehand, you can't really know where to pick. Yeah.
Is there a certain T we can usually be reasonably confident that we're close enough, or is it different?
Is there usually a what, sorry?
A typical like a T.
Oh yeah, that's yeah, there's like results that's saying like in the worst case for your function, then like if you do this many iterations, you'll be this close. I don't remember the actual results, but like, yeah, usually what you do is you're just gonna literally like plot how your error, like what the difference between this point to this point to the next point is getting, and if the difference becomes smaller and smaller, then you're like, oh, I'm probably close to the thing. And you'll do this in the assignments, like you're gonna do a lot of, well, I mean, I'll do the plotting for you, but you'll get to look at a lot of plots after you implement things of how things are getting closer and closer to other things and stuff like this. And another question, which is how does WT plus 1 approach W star as t goes to infinity? Wouldn't t go to the value close to W star? I'm not sure, like this thing is just a point on the W axis, right? And that point is getting closer and closer to W. So W star is like, it's the point on the axis. It's not the value of the function. Right, the value of the function would be g of W star, maybe is the confusion. So we're always talking about like the actual inputs to the function. We're trying to find the input to the function that gives the minimum value of the function. So W star is the input to g that gives you the minimum of the actual function output. Okay, and there's another question, which is, so you mean W1 is the second gradient descent, but why are you finding W0 and W1? You already have g of W. What is the minimum, right? I'm like, yeah, so in general, like maybe here it's visually very kind of easy to see around where the minimum and stuff, but like you're gonna, like, you can imagine if I give you much more variables and stuff, you won't even be able to plot the function and have any idea of where the minimum even kind of like is around. And so there you're really just like, then you extend the math, you use the math, but you like visually can't you have no idea like where to guess and stuff. So yeah, this becomes much more like useful when you have much higher dimensions of things, because you can't just plot the thing and look at where the minimum is around. So you're gonna have to use these equations, and then but you use this intuition to guide you to tell you that like, oh, in this high dimensional space where I can't plot things, this is the story of what's happening, is that I'm getting closer and closer each step. Okay, but here's kind of the, okay, so I move on to the next part now, which is kind of, here's the caveat. So like, people can do this in higher dimensions too, but it turns out to be much more complicated and very expensive. Okay, so let me write what's happening. So we move on to this topic called first order gradient descent. And I put in brackets because when people say gradient descent, they really just mean this first order stuff. And this is stuff we're going to mainly talk about. And the stuff before is kind of like to build some intuition about like where things are coming from. But it turns out we're actually not going to be using this exact story and intuition about how to think about it. Okay. So there's this first order gradient descent. And like, what's the story? Well, the story is that it turns out that sometimes it is hard to calculate G double prime of W. Why is this even important? Well, you need to make the step, make the next step, you need to calculate G prime of W and G double prime of W. And it turns out to calculate this G double prime can be quite complicated in general, in particular when you're in high dimensions. So like, especially in high dimensions. So this is all you really need to know, is that it turns out this G double prime thing is like quite complicated to calculate if you're in high dimensions, and it actually turns out to be a matrix in high dimensions. It's this thing, like the word is, it's called a Hessian matrix. And there is like machine learning, like you can do it with this Hessian matrix and whatever, and the steps look very similar. Oh, except now they're in multi-dimensions and whatnot. But it turns out that for most machine learning stuff, you never actually end up calculating, and you just like make a kind of a guess at what it's going to be. Okay, what do I mean by that is that instead, now your first order gradient descent update, okay, I can make it super clear, hopefully, I just take the second order one. Okay. And what I do is now, since I said this thing's hard to calculate, so what I'm going to do is I'm going to take it and just like completely remove it from here. But I need some, like, I know that it's there. Like, if I knew it, I would use it. But I don't know what it is, because like I don't want to calculate it, it's too complicated. So what I do is, instead of multiplying by it, I multiply by something, okay, which is going to be kind of like my guess to what it is in some sense. Okay, and I'm going to call this thing eta of t, and I can change it at each time step. And guess what? This thing, okay, so this thing has an important name in machine learning, which you will hear and probably have heard if you looked into any machine learning. So this eta thing is so you can call it the step size, or you call it the learning rate. Okay. All we did is we don't know the second derivative. So instead we say, okay, like, right, we need to multiply this really by 1 over the second derivative. Well, let's just take a guess and say it's this eta thing, and what are you gonna, like, what's gonna happen is, in reality, what you do is you just try a bunch of random numbers for this thing. Well, not random, like you do a search over different ones, you plot them, you try doing gradient descent for all of them, and I'll go over all of this. But like you do gradient descent for all these different values, and then you just pick the one that did the best. That's what's gonna happen. And that's really what happens in machine learning world, is you just do a bunch of experiments with different etas and just choose the one that kind of works the best for you. Okay, we'll talk about that in very, very soon. And like, here's maybe the insight. It's like, if we knew G double prime of W, right? Well, then we would set eta t equal to just 1 over G double prime of WT, right? And this is exactly from what I said before. We would just use second order gradient descent if we knew this thing. Turns out we're not going to know it. Okay, and so we call this method first order gradient descent. And notice that the first order thing is a little bit deceiving. We are not using a first order approximation. Okay, the first order part here is just indicating that we're basically doing second order gradient descent. But what we've done is we've removed our necessity to know the second derivative. So right, this is what the first order part just means all we're using is this first derivative part of the update rule. Okay, so from now on, when I say gradient descent, it's always just going to be like this first order gradient descent. That's all we're going to deal with and stuff. And now I give you a new way of reinterpreting the previous examples we've seen with the second derivative and thinking of the second derivative as a step size, and why this like word step size or learning rate makes sense. And then after that, we try other step sizes. Okay, so what do I mean? I give you an example. So let's revisit the previous example, but think of it in a slightly different way. What do I mean by that? So we have g of w, same exact g of w. So right, the black plot is the exact same thing. We're still trying to approximate this minimum. This minimizer, I guess, w star. So yeah, we know the first derivative, we know the second derivative, and so on. And like w naught is still exactly the same, it's 1. Okay? And here, notice I've drawn a line instead of a quadratic or a parabola. I'm going to talk about that in a second. Otherwise, everything is the same. There's this w naught, which is where we have the same w naught as before. It's the number 1 and stuff like this. Okay. Now I want to calculate what is w1. Right? In first order gradient descent, this is the update equation to calculate what w1 is. So this is how I think of it now. I'm starting at w naught. Okay, here's like our new way of thinking about it. I'm starting at w naught. Right? This is what the equation is communicating to me. And let me just be clear what I mean by that is I took this equation here and I've just put it here for the case where t equals 0, right? So this is t equals 0. This is t plus 1, so it's at 1. So I'm looking at that equation and I'm giving you an interpretation of it. So I can think of this equation as I'm starting at the point w naught, right? And from it, I'm subtracting something, okay? So now I give you the interpretation of what is this thing that I'm subtracting from it. Okay, so let's look at that thing. So in here, I have this like derivative, right? And how do we think of the derivative of a function? Well, we can think of it as like the rate of change of the function. Okay? And in particular, you can plot it as like this line that goes through the function at the point. So this is going through the function at the point. And that line has the same slope as the derivative. So this is, and that line turns out to be called a tangent at w0. All it is just a line that goes through this point and has the same slope as g prime at w0. Okay, so now I can think about this as like kind of the rate of change in here of this function there. Great. And now I somehow want to know, like here's like my goal is I'm at w0 and I somehow need to move to w star. Okay, so like it turns out that this rate of change thing actually gives me kind of the direction I need to move. And what do I mean by direction? So what I need to know is from w0, should I move left or right? So in the 1D case, it's very simple. It's just left or right. In 2D, you would have like more directions and stuff, but like all the ideas are going to transfer. So in 1D, I just need to know, do I move left or right? It turns out that exactly this rate of change of the function is going to give me exactly this direction. And what I mean by that is the rate of change here, right, like the slope is positive. Okay, and it turns out that in general, this like derivative g prime gives you the direction, like if you look at the fact that it's positive, I would say that that's like to the right. Right means like positive means move to the right. Okay, so the rate of change of this g prime gives you the direction at which the function, like the direction to move for which the function is increasing. Okay, so positive slope here, like at g0, means that I move right, and right always, like this rate of change always tells me the direction to move to increase my function. Okay, so if I move to the right, my function g is increasing. Okay, it turns out we're going to need the negative of this. This is where the negative comes from in a second, but think about the other way. So if I were to draw the tangent line, let's say here, at like maybe minus 1.5, maybe I can briefly draw that. So I draw like a tangent line, and that has a negative slope, right? And then I interpret it this way, like negative slope means that if I take the direction of the negative slope, so the negative means move left. And if you look, moving left would cause also the function GW to increase. Okay. So there's this like, here's the idea, which is that the G prime gives the direction of ascent for the function G. Okay, so this is basically the intuition that ends up drawing is like this G prime in this 1D case is just like whether it's positive or negative in multiple dimensions, there's gonna be positive and negative in all the different directions. But this gives you the direction for which to ascend the function. Basically, if I go in that positive or negative direction, then it gives me the direction to go and increase the value of the function. Okay, but recall that like I want to find a minimum, so I need to go in actually the complete opposite direction. So I need to go into the negative direction of ascent. And this is where the term descent comes from, right? This is like I am descending in the negative direction of the derivative. And if you remember in 1D, the derivative is the same as the gradient. Okay, so here's the gradient descent part. I am basically descending in the I'm using the gradient to choose my direction of descent. Okay, so all that being said is that this gives me the direction of ascent. This negative gives me the direction of descent. And then I interpret this as telling me how large of a step am I taking in that direction. Okay, so this is why it's called like the step size. How large of if I make this big, then I'm taking a big step in the direction of descent. And if it's like small, then I take a small step. Okay. So there's like the intuition stuff. So now what happened? So like what happened is that I plotted this thing. I started at W0. I chose some value for this step size. Turns out I chose exactly the second derivative one. So now I'm just giving you the interpretation of when I actually know the second derivative and I plug it in or whatever. But now I give you this interpretation of it, thinking of it as taking steps based on the gradients, which is this value would turn out to be something, and whatever that value is, I subtract from W naught. Okay, it actually turns out to be very simple in this case because this thing was 1, if you remember, and this value turns out to also be 1. Okay, so my step is of size 1 in the negative direction. And then I end up with 0, which is what this W1 is. So I end up from here. So you think of like I start at W1 and I take a step to W1. Or sorry, I start at W0, I take one step and I get to W1. And then, unsurprisingly, the next part has like a similar story. Oh, yeah, okay, this is good actually. So the next part is I can then, of course, start at W1 and then take a step to W2 in the exact same way as before. So this is the update from W1 to W2, right? I started W1. And from it, I'm going to like subtract something. And that is a step of this size. And then this thing gives me the scaling of my step. So, and then visually, this looks like I started at W1 and I took a step to W2. So you can think of this like whole first order gradient descent thing as stepping in the directions of the negative gradient. So descending down, this is called like descending down your function. So you're kind of going down your function. And then you get to your next point, W1. And then from W1, you're going to the next point, and so on and so on. Okay. I let you think about that for a second while I answer another question, which is, for the step size, why is it 1 over 2 plus e and not 1 over 2 plus e to the w? Oh yeah, so the reason I just chose 1 over 2 plus e is because w naught is 1, so e to the w naught is just e. So I've already plugged it in. Technically, this is like 2 times 1. Oh, technically, this is 2 plus e to the 1. I've just plugged in W naught. Okay, so here's some more. Yeah, I can answer the question.
I think the step thing, right, is because we're using the step size is because we don't know G double from.
Yeah, I'm gonna get to that right away. So so far, notice that I said we don't know this, but then I used it. The only reason I used it here is to just give you the same exact setting as before, but different way to think about this multiplication term in the front. So right, we had this interpretation before where you think of it as you think of actually approximating your function with a quadratic and then finding its minimum. Another way of thinking about it is just simply looking at this equation that you get after solving the derivative and stuff, and just interpreting it as taking steps. And then you would think of this term as simply being the scaling for your steps. Okay, that's all I was trying to say. In general, you don't know what this is. Or like we're not actually going to use this. And so that's exactly what the next plots are going to say, which is like, what happens if I, let's say, okay, like let's have some understanding of what happens if I pick a small value for it or a big one. This is like the classic way you think about things, like try that both extremes. So I start with something small. This actually isn't that small. Maybe I could have chose something smaller, but the story holds. So I chose, in particular, this thing is small in the sense that this is smaller than 1 over 2 plus e. Okay, that's what I mean by small. It's smaller than the actual like best value that I could have had, which is that 1 over 2, 1 over the second derivative. So what happens? Well, then your steps become smaller, as you would expect. So here, look at the steps. They went from here to here, and then from here to here. Now the steps have become smaller than above. Right? This is a smaller step to W1, and then this is an even smaller step to W2. And you would what happens? You need to take more steps to get to W star. So you'd want to take like a W3 and a W4 and so on to get to W star. And when does this happen? This is when you're kind of like your guess for the step size, right? Because at the end you don't really know what to pick. You're just going to pick something. Is actually much smaller than the correct kind of like second derivative guess. And then you could try the other extreme, which is like, what happens if you pick the step size to be too big, right? And something too big here is like something that's obviously larger. And maybe I don't put the equal to sign. Something larger than 1 over 2 plus e. And this is quite a bit larger. And then your steps become very big. In particular, the scale here has even changed. So here we had -1 to 1.5. And now the scale had to become bigger to even fit the steps. And notice W0, so this is the same W0 as before. So it's still W0 equal to 1. But now look at this first step. The first step went from W0 to W1 all the way over here. It like completely overshot W star. It completely missed this guy and went all the way there. And then from W1, you take another step, you go to W2, which overshot W star again. And it turns out if you actually repeat this process with a step size of 1, you're then going to get something even bigger, and then something even bigger. And what's going to happen is you're never even going to reach W star. And this is called diverging. Okay. So the point of showing these two examples is to communicate that this step size like has exactly the interpretation you'd think, which is tells you how big your steps are from each one of these points, right? And if you make it small, it turns out things are like, you're kind of safe, but it's going to take long to get somewhere. Okay, so like maybe I write this, which is small step size is safe in the sense that you will probably converge. And converge just means like after you do many iterations, you'll get to converge to W star. However, it might take long. Okay. That's the first point. And large step size can get you to W star fast, but sometimes it might diverge. So it completely depends on the particular like function and stuff you're trying to optimize. If you make some guess of a step size, if you make some good guess, and by good I mean like something close to this actual second derivative thing, then you're going to converge fast. But if it's too large, then you might diverge. But if it's too small, you're like safe in the sense that you're at least making progress to the right direction, but you just may take much longer to get there. Yeah. Yes, so you can do this thing called like, and we're not really going to talk about it in this class, but like you could just, and it's the most naive thing you could imagine, which is you just start from like a small step size, and then you just like calculate this equation, this step, and you do it like, and then you see, okay, like I didn't take too large of a step from before, like my function still got, okay, what do I mean by that? I mean like, I start from here and I choose some like step size, and we're not going to cover this, but like, I make the step size, I start with something really small, right? And so then I take like a tiny, tiny step, and then I'd look at my function value. So maybe it's here, and I see, oh, it still got smaller. So maybe I can increase my step size. So then I increase the step size, and I calculate again. Maybe I go like to here, and I see my function still got smaller. And then I do it again, and oh, my function still got smaller. Then I do like a much bigger step, and this is all just like you're testing. You still haven't actually calculated anything. You're just like checking all these things. And then you take a much bigger step size. Maybe you go to like here, and your function value, okay, I go here, and your function value actually got bigger. So then you'd be like, okay, I use the last step size I just checked that actually got me smaller, or like that didn't get me bigger. So that's kind of sorry. And then that's the actual step size you use. And you do this after every step, but it's like quite computationally expensive to do this check every time over and over again. But yeah, there's like, okay, we're going to talk about how to set step size, and there's like kind of rule of thumb options, and we're going to do some simple ones. And then in the assignment, you'll try all these different things, and you'll plot them and see how like they work in practice and stuff. But yeah, there's like, it's really a function of like, if you have a very simple, naive way to pick the step size, you're gonna suffer no like computational cost. You just make a guess, and then you can just do it. And then as you get more and more complex and like sophisticated methods for picking the step size, and as they get closer and closer to actually being the correct step size, it's gonna cost more and more computation, but the steps will be better. So there's gonna be this trade-off between like quality of step versus amount of computation you want to take before taking each step. Right, and we're going to talk a lot about computation actually later on. But this is like, yeah, this is the high level idea. Yeah. Yeah. Sorry? Yeah. Oh, yeah. It definitely should be. I like, in the plot I did it right. Like in the plot, it actually used e to the 0, which is this. But I wrote it wrong, so. So that's what happened in the plot. Yes. Very good point. So this is like this is what it means by 1 is actually different than the 0, 1. Like it actually uses the values there. It actually uses this thing. Like this is where the time dependence is. And like in the most naive thing, which we'll talk about as well, is like you can just pick eta to not even depend on time. Just have it like one number all the time. Which is what we did here, right? We just chose a number. We didn't even have it depend on time at all. And yeah, okay. So I answer one last question, which is, so what do we use the direction of ascent for? Yeah, we use the direction of ascent for exactly the fact that like, yeah, if we look here, for instance, if you were to draw this thing, right, you would draw this. This is a line. Okay, I draw the line. You would draw the line. And notice that here we took a step to the right. How did we take a step to the right? Like what I mean, went from W1 to W2. How did we go to the right if I told you the update was minus here? Well, it's because the direction was also minus, right? So I told you this direction thing tells you the direction of ascent. In this case, the slope is negative, so you get a negative direction. And that tells you, so the negative direction would mean like going left. And left tells you going up is ascent. Okay, so the negative slope tells you negative direction is increase. So then we do the descent part, which is take the negative of the slope, which in this case would be the negative of the negative. Okay, so you would have negative times the negative slope, and then you get positive direction. Okay, so that's why this step can be positive. Yeah, so the derivative really tells you the direction of it. And I'm doing this 1D case where just like negative is left, positive is right. In the multidimensional thing, like you have each one of the indices actually telling you which direction you're going. It's more complex, like visualizing and stuff is more complicated, but the intuition stays the same. Okay, now we do multivariate version. This is actually the case. What is this? Oh, I know what this is. Okay, yeah, so we do the multivariate case. And maybe I make a new page. And this is the real deal in machine learning, I guess. This is what we're actually doing. Yeah, remember we had these, like in machine learning, we had these linear functions. There was this weight vector, it was d-dimensional. So we need multivariate case. So multivariate And I'm writing gradient descent, and of course, this just means first order gradient descent. And it turns out the story is exactly the same, which is great. So now you just have W vectors that belong to the domain W, which now is RD instead of just R. And here, in particular, it's RD greater than 1. Otherwise, if it was 1, you'd have the univariate case, which is what we've been studying. Okay, and then remember, we have now like this G, our G function is now a function of this W vector. Okay, what's our new objective? Well, I mean, it's not really, it's the same objective as before, which is, remember, our objective is to find the W star. Now it's a W vector star. And just remember, this thing looks like W1 star, W, oh, yeah, dot, 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 up to W D star, right? There's now just D dimensions for the vector that we need to solve for. And this is the minimum, right? This thing has a definition. We want the minimum vector that makes this G of W function the smallest. Okay, that's what it means. The smallest, the minimum, yeah, same story. So now, like first order, or so so now we have the gradient descent update rule. So this is the exact same rule as before, almost too. Okay, so we want to find W star. And how did we do it before? We just took these gradient steps and iterated over and over. And as t got closer to infinity, we got something closer to W star. Now we're going to have the same story, except we're going to do it for each dimension like one by one. So we can think about taking steps in each dimension, kind of like separately. Okay, so we're going to have the following gradient update, and we're going to update the whole vector at once. And okay, you'll see in the examples how to think of it in each dimension. So it's the exact same rule as before. The teeth plus 1 weight or value is equal to the teeth value minus the step size. And here we're just going to think of the step size always as just a number times a vector. And what's that vector? The vector is now going to be the gradient. And now we really have this full like gradient interpretation of things. Here's the gradient. Here's the minus the gradient. That's the descending part. So gradient descent, and you're descending with steps of this size. And the interpretation is kind of the same. You start with some point in multiple dimensions. And from it, you just take steps of this size. Okay. And they're descending steps. They're going in the negative direction of ascent. So that would be the descent direction. Okay, now I just give you the definition of this gradient to remind you, because we're going to need it. So this is literally just straight from the calculus part of the notes. But I remind you what it is. What is the gradient? Well, it's what we've been calculating before in this like closed form stuff. It's really just the partial derivatives of the G function for each dimension. Right, and now here, notice I'm putting the W vector. Emphasize, this is what I said at the very beginning of the class. And it's just all of them put into a vector. So it's all the partial derivatives put into a vector. And we've done these type of calculations before. Excellent. Now, this thing is in RD. Okay, so all we've done is literally like, before we've been working with one dimension, so you can think of it as like we've taken its derivative, and then that was the one dimension. Now we just have it arranged in a vector, just like a comma separated thing of just each one of the derivatives. And now look at the steps. The steps are just this vector minus this vector, which is your starting point. And that gives you a new vector, which is your like the point you end up in after taking a step. Okay. So of course, I show you an example to visualize what it means to take steps in multiple dimensions now. And we start with this function, which is very similar to before, except now it's a multidimensional case, but like, so here we have 2 dimensions. And okay, I'm going to use 2 dimensions for this multidimensional stuff because in 2 dimensions, we can still visualize things, right? You still have two axes, like the X and Y axis, and then the Z axis can be the values. If we go to anything more than 2 dimensions, it's going to be hard to visualize, but the story stays the same. So it's always the case that in multiple dimensions, we get intuition from the 2D case and then just use that intuition for higher dimensions. Okay, so here's our function. It's now a function of like a vector. So this vector has components W1, W2. Okay, And the function is just almost like the one before, except now it's the same, like it's the case where it's the function we saw before in one dimension, so for W1, and a similar function for the second dimension. Okay. So yeah, like we have this object, and so now let's calculate the gradient steps, like what they would look like. So let's do this calculation, and then we'll plot them. So to do this calculation, I need the gradient. And to calculate the gradient, I need the partial derivatives. So we start with calculating the partial derivatives. So the partial derivative of g with respect to W1, what is it? Well, I look at these things don't depend on W1, so they're constants. So then it's just exactly the function we had before, which we've taken the derivative of already. And now it becomes 2 times W1, and this is a 2, not a del, plus e to the W1. Turns out it's the same story for W2. Two times W2 plus e to the W2. Shouldn't be anything special. It's what you've seen already in the 1D case. What does our step look like? And I write this now with column versions of vectors to like make it more clear. So this is our step. Now I'm going to write this out explicitly. So we want to calculate where are we, like what point do we get to at time step t plus 1, or like iteration t plus 1. What does this thing look like? This is a 2D vector, right? It's going to be w of t plus 1 index 1 and w of t plus 1 index 2. Oh. And all I've done is written the vector in column format. So instead of writing this transpose business, I've actually written it as a column. And the reason is to communicate what does it look like to take a step, and it should be more clear. So what does the update look like? It says that this vector looks like some starting vector. This is our kind of like our starting point in time at iteration t. That's just this wt vector. Right? And from it, we take a step, which is going to just be like subtracting another vector, which is exactly the amount of step we want to take. And that other vector is going to be some scalar eta t, which is our step size, multiplied by the gradient. And what's the gradient? Well, it's these partial derivatives we calculated above. So it's 2 times W1 plus e to the W1, and 2 times W2 plus e to the W2. So that's our step. Oh, and the thing we're missing is that this is the values at time step t of these guys. Excellent. Okay, so now let's actually choose some starting point at iteration 0 and see what the steps look like. So suppose we chose the initial, like our initial starting point, W0, to be the vector 1, 1. Right? Before we chose it to be just the number 1. Now it seems kind of just natural that we would pick the vector 1, 1. And let's suppose we choose the step size to be like before, like 1 over 2 plus e. I don't know. Okay. So now, what does this step look like? Well, the step looks like W1, right, equals to the initial point, 1, 1, minus the step size, which is 1 over 2 plus e. That's just a number, a scalar, multiplied by the vector. And for this vector, right, I'm plugging in W10, that's this 1, and then W20, which is also the number 1. Okay, what I get back is 2 plus e and 2 plus e, which turns out to just give me 1, the starting point minus 1, 1 equals to the 0 vector. So this is where I'm expecting to get to after my first step. And it turns out I can also calculate W2. Okay. And for W2, okay, so I suppose that I also then use eta 1, because this is actually what I did in the plot. I keep it at this. I didn't actually change it or anything. I just kept that at the same thing. Well, then W2, I don't fully count, but it turns out to be the 0, 0 point minus 1 over 2 plus e Now with the corresponding 0 plugged in, so this is 2 times 0 plus e to the 0, I believe. Right, it's 2 times 0 times e to the 0. So it gives you 1, 1. Okay, so that's what we get. That's going to be our W2. Okay, so visually, what does this look like? Here's what it looks like. Okay, so here's the 3D visualization of what happened. So I'll give you some 2D ones in a second to also interpret this, but we start with this one. So W0 is here. And what was it? W0 was 1, 1. This is like, so it's a 3D plot, so like this is kind of like curved up, you know? So it's like this thing really is at 1, 1. It's just like, since this thing is curved up, it doesn't look quite like 1, 1. But anyways, this is at 1, 1. You then take a step in the negative gradient direction, which is the direction of descent. The gradient would actually give you this direction, which is the direction of ascent. And we'll see some plots to help with this as well. And we get to W1. And then from W1, we take another step and we get to W2, and so on. And the minimum is somewhere like here, which I guess I haven't put. But the minimum is something like here. And so we're approaching that minimum, as you would expect, but now in 2 dimensions. Another way to visualize this is by drawing some 2D plots. And maybe we start with the one to the right. So the one to the right actually shows you, so this is just like a top view of the space. And you can see that the orange W0 is actually at 1, 1. Okay, so I'll tell you these arrows what they mean in a second. Then you take a step to 0, 0, as you would expect. And then you take another step to whatever this minus 1 over 2 plus e and minus 1 over, so that's what this purple thing is. So you've taken these steps. Okay, that's how you can think about it. The arrows are indicating the negative gradient directions. Okay, so at this point, the negative gradient is pointing this way. At this point, it's pointing this way. At this point, and the size of the arrow tells you the kind of the magnitude of the gradient. So, right, because this, at the end of the day, this thing is not only telling you a direction, it also tells you like the scale of in that direction, kind of the proportions. So yeah, so yeah, like you can see at this point, the gradient is going this way, so, or the negative gradient. And so what do we do at this point? We follow the gradient. So we're descending down the gradient path. We get to here. The gradient is smaller, but it's still there. So we take a smaller step and so on. So this is a really good interpretation, this plot with the gradients. You can see that if we started here, you would then know that you would take your first step this way. If you started here, you would take your first step here. And so you can see that depending on where you start, you just look at the gradients and then go, and well, the negative gradients, and you go in their direction. Okay, so this is like maybe the most important interpretation of it. And then in higher dimensions, you just think that, oh, in 2D it would look like this, so in higher dimensions, something like this is happening. And all that this plot is on the left is it's a heat map where here, this is the actual values of the function. So 1.5 is like, you can see this is the minimum value of the function. This would signify this kind of like area in here of the plot. And then it's just like these contours around it is basically what we're plotting. And we could see we started at a large value, maybe around like 9 or something. And then we got to a smaller value, something like 4 maybe. And then we got to an even smaller value, and so on. Okay, so this was a nice simple function. I give you another example with a more complicated function, which I don't do calculate all the steps, but you can imagine, you just solve those same equations. In general, you would do that on a computer, so you don't have to work it out manually and stuff. And that's what you do in the assignment. And here's more steps. So I've always talked about 2 steps, right, so far. But in general, you're gonna want to do maybe more steps if you haven't quite got anywhere close to the minimum, just with 2. And so here's an example of, yeah, some more complicated function. You can see there's like W2 and W1 are dependent and squared and whatever. The point is it's more complicated. It's got this like complicated looking structure and stuff. But here's what happened. We started at W0. I took some guess at what W0 was. I don't actually remember what the values of this, or what the guess was, but you can, like visually you could see I took some guess. It clearly was not the minimum point, which was around here or something. And then I took some steps, and then the first step descended further and further down along the gradient, and we got to the final point, which was here. And if I kept iterating, I would get closer and closer to the true minimum, which maybe is somewhere like here. I don't know. And I give you the 2-dimensional plots as well. And hopefully the gradient thing should also give some intuition again, which is we can see These are all the gradient directions. Here, the gradient is very large. Makes sense. The plot was really steep here. And it gives you the direction, which is going down this thing. And so that's exactly what we see. We see this point goes this way and so on and down this slope. And yeah, and at this point, you could see the gradients are like very, very tiny. These arrows, I don't even know where they're pointing anymore. Okay. And the intuition for the step size stuff is also the same. Like if I chose a really big step size, then maybe my first step would have went all the way over here. And if I chose a smaller step size, then like maybe I wouldn't have got all the way here. Maybe I would have like I wouldn't have got this far. I would have maybe only got like very tiny little steps and maybe only got to here after these 9 steps I took here. Okay. But what I did, like, how did I do this? I tried different step sizes until I found one that visually looked reasonable. Like originally, when I took a guess at the step size, I was like barely moved. Like I had all these x's were like on top of each other. Then I tried a bigger one and it jumped all the way to like here. And so I did exactly what I was telling you. I just searched through some different step sizes and found this was a reasonable. I think I chose something like 1/6, simply by searching. Okay, so this is yeah, this is good. That's all we had for the plotting stuff. So now I think yeah, okay. The next thing I was going to talk about was selecting the step size, which is like, I guess, very natural next thing to discuss. And I write the title and then I answer questions. Does the step size stay the same for each calculation? Like you can change it. We're going to talk about it exactly now. I just leave it. This question, is it like the genetic algorithm? I don't know what the genetic algorithm is, but this is a machine learning algorithm, I guess. I don't know. Okay, let's do step sizes. So these are like some maybe common and simple options. Okay, I put in brackets. There's more complicated ones, but like all you need to know is that the more complicated ones, all they're really doing is trying to get closer to what the second derivative is without too many like computational steps. Okay, and for here, like obviously the t is just an element of the natural numbers like throughout. I don't know, I guess I've said this, you guys understood this before as well. Okay, so I give you 4 options, starting from like the simplest to maybe slightly more complicated. So the simplest one is just like the constant step size. And that means that eta of t is just equal to a number, and that we will call just eta. And that's an element of 0 to infinity. So notice here I'm saying that like, okay, if I didn't include 0 in this interval, because if I included 0, then you would take no step at all. You would take a 0, you would just be stuck at the same point. So you should pick something larger than 0. And then, yeah. So it's just a number. And so in this case, I actually used just this constant step size. And you can see it did pretty all right. Like I got somewhere. And this is not so uncommon in machine learning, actually. You have just like a really safe classic bet or like choice is just pick a constant step size, but pick it really small. Maybe something like 1/1000, 1/100. And yeah, and then try that. 2. This is a little more interesting, which is called the inverse decaying. There's probably other names. And the idea is the following, is like, as you're getting closer and closer to like the point, you want to take smaller and smaller steps. That's really all it's doing. It's like, when you're getting closer and closer to this lower point, you shouldn't be taking gigantic steps anymore because you're closer. So you decay with time. And the nice thing as well, as I'm writing about this, is like, if you chose a step size too large at the beginning, then maybe you were making really big steps at the beginning. But then over time, you start making smaller and smaller steps, and eventually you do end up getting to the minimum, even if at the beginning you were like overshooting the minimum point. Okay. And this step size is really just 1 over your iteration time t scaled by some numbers that help you basically tune this thing when you're actually using it. So what that means is like, if you just think of this thing as a number 1 at the top, then you can, and forget about this number 1 and forget about this lambda, then you just have the equation 1 over t. And so as t increases, the step size gets smaller. And then all we have here is like parameters like this eta that allows you to tune how large it is, and then lambda to multiply this thing, how fast you're decaying. And then there's a 1 so that you don't divide by 0 in the case of 0. That's basically it. But the point as like approximately equal to 1 over t. And then you can tune how much you're scaling by. Okay. The third one is very similar, except the way at which you're decaying is not 1 over t, but 1 over an exponential function. So you have an exponential decay instead of this like inverse decay. And it turns out like, depending on your case, one is better than the other sometimes. Once again, this is usually in practice, you just experiment or someone will find that for certain type of problems, this is better than that. So then people just always use this for that kind of problem, and that's it. So very okay, there is theory behind some of this. Like, of course there's theory, but like a lot of time you can just experimentally test these things. Okay, and so this one also has this like scaling factor of eta, but now instead of 1 over lambda t, you multiply by, okay, I write it as 1 over e to the lambda t to make it very clear. And yeah, these things are as before. Just parameters you can use to tune the rate. You make lambda bigger, you decrease as t increases faster. You make this larger, you start at a larger point at the beginning. That's it. Okay, so these were both had very similar ideas of decaying. They're just decaying with different types of functions. One's 1 over exponential, one's 1 over t. Okay, the third one is slightly more interesting, which I will call the normalized gradient. And this gets much closer to like something that actually gets used, so something slightly more sophisticated. And it has a similar idea to some slightly more complicated step size techniques. And the idea is that notice that the gradient is really, really large here, right? Okay, the gradient is sometimes really large. And when it's really large, what does your step look like? Your step looks like 1 minus, okay, your step size, but you're also scaling by the corresponding gradient. So if your gradient's really large, maybe you should like, your step size should also look at that and make sure your step isn't too large at the same time. So what I mean by that is like, if your gradient's really, really steep, you might take a giant step here, right? The step might be like, from here, it might be enormous because the gradient's really large. So what you would want to do is have the step size as 1 over the gradient. Basically scale by how big the gradient is. So like if you have a really big gradient, then don't take then have your step size to be smaller to account for that. And if your gradient is smaller, like here, then take a larger step. Because like you're barely moving here, so then multiply by 1 over the gradient, and since the gradient's small, you multiply by something bigger. So basically it just accounts for the fact that, yeah, big gradient, take smaller step, small gradient, maybe take a slightly bigger step. So yeah, this thing has a similar look as well. And it's this eta, then you have this epsilon instead of a 1. Sometimes we put an epsilon, but it's just to make sure you don't divide by 0. And then here you add not the gradient because you just want a number. You add what is called the 2 norm, or kind of like the magnitude of the gradient. And you may have learned about this in in linear algebra before. But it just measures the size of your gradient, like how big is it? Okay, and I give you the definition in a second. So once again, these guys are just kind of like parameters. But the epsilon really has like a special property here, which is like epsilon is usually very small. And it's just there so you don't divide by 0. Because if you didn't have this epsilon, then if the gradient is 0, you'd be dividing by 0. So for example, you would set some epsilon something like 10 to the minus 8. Okay, so really then, what is this normalized, or what is this like great magnitude of the gradient term? Well, this thing is something, well, it's exactly like, people call this like the Euclidean distance of a vector, or the 2 norm of the vector. It just measures the size of the vector. And what is it? Well, it's exactly the, so, okay, you remember this gradient. What does it look like? It's just a vector, and it has terms like this. And if you have a vector and you want to calculate like its magnitude, what you do, or like its kind of its Euclidean distance and stuff, or size, what you do is you take all of the components and square them. Okay, so what are the components? The components are the partial derivative of g with respect to wj. You take every one of the components and you square them. I guess we need the t here. You square this thing, okay? So that's just one of the components. So you then need to take every one of them and square them. And then you take their square root. Okay. It's just like in 2 dimensions, it's like if you have some vector, you square each one of its directions, and then you take its square root. That gives you like basically the hypotenuse in 2 directions, 3 dimensions, and so on. That's all it's doing, but it gives you the size of the vector, is the point of the story. Yeah, that's all I want to say. And like the intuition was that like when the gradient is large, then maybe you should have a step. Oh, this guy is, of course, the definition of the step size. So maybe your step size should become smaller. So gradient large, you multiply by 1 over the size of the gradient. So you don't want to take 2 large steps then. Okay, these are basically the 3 step size methods we're going to discuss in this class. And maybe I just leave you with the title of what the next section is going to be, which is, it's going to be gradient descent, but with a very specific function, which is the estimated loss. And so now we finally move into the machine learning part, which is we're going to do gradient descent for this estimate of the expected loss.